Okay, so today what we're going to learn about is enthalpy. So we introduced thermochemistry in the last video. We talked about how it's, we're looking at the internal energy of systems. Okay, and internal energy is really the work done by a system plus the heat. So okay, and that gives us the internal energy, or the total energy that a system can do. So with chemistry, though, most of the time the work done by the system in an open container, and most chemical reactions, happen in atmospheric pressure and stuff like that. We really don't need to worry about it too much, okay? Because the work is just the volume and the pressure changed. And if you think of, when a gas is being produced in a reaction, the volume changed on the surroundings via that gas being introduced is pretty negligible. So what we're going to introduce is this new term called enthalpy. Okay, so enthalpy is what we are going to use to talk about internal. I'll put it in quotations. Internal energy. So the internal energy of a system. So with the chemical system, let's talk about what we're really talking about. Where is the energy stored within a system? Okay, so if I look at something like methane, okay, so methane has these bonds. Okay, so there's energy, or there's an attractive force that's going on between carbon and these hydrogens. Okay, so they want to be by each other. You have the protons from the carbon attracting these electrons, and then you have the protons from this hydrogen attracting these electrons. Okay. So there's a bond there, and that bond has been formed because it's a stable state. So this is a low state of energy. That's why bonds get formed. You can kind of think of it like this. As two atoms, say we got two hydrogen atoms. Okay? Well, we know in nature that hydrogen exists as H2, or a hydrogen bonded to a hydrogen. So let's say we've got two hydrogen atoms really far apart from each other. And here's our scale. So let's look at the energy versus the distance. Okay, so we have two hydrogen atoms really far apart from each other. And as they get closer to each other, so this one moves in and this one moves in, they start to become more attracted to each other. And we know this because eventually they form this bond and make H2. So if this is our zero thing for attractive energy of attraction, or potential energy, okay, when they're really far apart from each other, there's no attraction. Okay? But as they get closer, they start to say, hey, you know what? You got an electron, I've got an electron that we can share. So they start kind of getting lower in energy. Okay? Because they're pulling to each other, so they're becoming a lower energy state, or more stable. And then eventually they get to the point where those orbitals overlap, and they're down here at the bottom, and they've become more stable. Then as they push on top of each other, the nucleuses start to repel each other, and they become less stable, right? Because they want to push back. Okay, so as we're looking at this graph, here's this kind of idea, and we'll get that back to bonds, and how does this relate, and why do bonds form? So things like to be at a stable energy state, right? So if I pick up something really heavy and hold it up high, it takes a lot of effort for me to hold it up, and it takes a lot of energy for me to hold it up high. Now, the easiest thing for me to do is just put it back on the ground. Okay, that's the lowest or the most stable energy state because it takes the least amount of energy. Okay, the same thing is true for bonds. Bonds like to be, or chemicals like to be at the lowest energy state possible. So for hydrogen ion atoms, what we have is when they're really far apart, there's not a lot of attraction. But as they get closer together, they get more attracted to each other. And since they want to get more attracted to each other, they're going down to a more stable energy state. Eventually they reach a point where those bonds are stable, that bond is made, and we're at the bottom of this, at the most stable energy point, and they want to stay there. And that's why H2 stays together. The reason H2 forms a bond, or any chemical forms a bond, is because they've gone to a more stable or lower energy state. Okay? So with chemistry, what we're talking about with enthalpy and stuff is we're saying, okay, well, how much energy is stored in that bond? Okay, how much energy is given off when that bond is made? And also to break the bond, right? If I want to break this bond, what do I have to do? I've got to pump in this much energy to get those hydrogen atoms to pull apart from each other. You know, if you think of it with like magnets, okay, as two magnets get closer and closer together, eventually they get close enough that they actually, okay, so two magnets, all right? So right here, there's not a lot of, there's some pull, but they can, you know, as they get closer, what do? Eventually, they stick together. Why? Because that's the most stable energy state they are. Now, if I want to break this, I've got to put in energy and pull it apart. Okay, so when we're talking about enthalpy, or internal energy of a system, what we're talking about is the difference between the bonds, how stable these bonds are versus how stable the product bonds are. Okay, so that's what we're really measuring with these reactions. So let's say we have a combustion reaction. So CH4 plus oxygen goes to carbon dioxide plus H2O. Okay, so we're just combusting some methane, right? Put 2 there, put 2 there. Now we have a balanced chemical reaction. All right, well, we know with a combustion reaction that it gets hot, right? Okay, fire is formed. So last week we talked about, well, if it gets, or last video we talked about if it gets hot, I'm also adding heat as a product. Well, what does this tell me? If I'm adding heat here, that means the system has given off energy, or all the bonds for the reactants are at this energy state. And then as the reaction happens, the bonds of the products are down here at this energy state. So they're more stable, okay? They're at a lower energy state. This is energy. Well, what results from the difference from going from the reactants down here to the products? This is energy that leaves as heat. Okay, energy that leaves as heat. And this is what we're going to start measuring and look at. And this is how reactions are studied. We don't know the absolute energy of these chemical bonds, but we can tell the relative difference based on the energy that is produced in a chemical reaction or the energy that is needed to put into a chemical reaction for it to happen. And how we're going to do that is by enthalpy. Okay, so enthalpy is going to become kind of our internal energy of a system. It's not completely true because we're just dealing with the heat, but that's what we'll say. We'll say enthalpy is kind of the internal energy of a system, or how much energy those bonds are actually holding. Okay, so let's take a look at one other thing here real quick on this video. Okay, so let's say I'm forming water. Okay, so let's say we have this reaction right here. This is a redox reaction, by the way. Okay, first off, is water pretty stable? Yeah, you know, there's a lot of water around. So when hydrogen and oxygen come together, they form water. Okay, you've seen this, and this is a pretty easy reaction to happen. If you think last year when we blew up that balloon with hydrogen and gas, and then I caught it, lit it on fire, this is really the reaction that was going on. You have hydrogen plus oxygen going to water. If you also remember that, it made an explosion. Okay, so we know that, hey, plus heat. Heat is added to this, or is a product of this reactant. So if you think of the enthalpy of the reaction, because remember, enthalpy is measuring internal energy. Okay, so let's say, I did not spell enthalpy right there. Let's think of the enthalpy of this. So what happens is the reactants start at some energy level. Their enthalpy is up here. Okay, as they form products, they go to more stable bonds. Okay, so the amount of energy in these bonds, okay, it takes more work for those atoms to hold on to those bonds than it's going to take for these bonds to hold on. So what happens is my energy, or my enthalpy, drops down here to my products. Okay, so my products are at a more stable energy state than my reactants. And what we see here is that the change in enthalpy, okay, is actually decreasing. We go from a high state of enthalpy or energy to a lower state of enthalpy or energy. So my enthalpy change, delta enthalpy, is actually going to be less than 0, right? Okay, because it decreases, like, you know, if you did products minus reactants, it decrease, have a negative change. The extra energy goes out as heat. So that's what we're really dealing with here. Now, the thing about this is heat is really easy for us to measure, because all we have to do is we have to worry about temperature change. If something is changing its temperature, right, it's being heat added to it or heat taken away from it. And that's why we use enthalpy instead of worrying about, if you come back here, internal energy is really work plus heat. Work's sometimes challenging for us to measure, but heat is pretty easy for us to measure. Okay, so this is what we'll start looking at with chemical reactions in thermochemistry. What's the change from my reactants to products? Is heat produced or energy leaving the system into the surroundings, or is heat needed? You know, the reverse of that reaction, let's say I wanted to decompose water. Well, this just doesn't happen naturally, okay? I have to put energy into this. So one way you can do this is you can put electricity into water, and you can separate out water into oxygen, hydrogen. Well, in order to do that, I have to add energy. And why do I have to add energy? Well, if we look at the enthalpy again of the reaction, what happens is my reactants are down here at this energy level, and my products are up here at this energy level. Okay, so my products exist at a higher or less stable state than my reactants. Well, how do I get up there? I need to add in energy. Okay, so you add energy in, or you add in heat to the reaction, and that's how you get that to go. So enthalpy. One other thing about enthalpy. Enthalpy, I'll give you the whole formula for it. Again, not that we're going to use the whole formula, but enthalpy is represented by an H, okay? And most of the time, since we can't really measure absolute energy, but what we can measure is the change, okay? So we can measure the change from the products to the reactants every time. Hey, how did the energy change? Was heat produced or was heat needed? So most of the time we'll be worrying about delta H, and it's equal to the change in the internal energy of the system plus the pressure times the change in volume. Okay, but the big thing here is when we talk about delta H's, we're talking about the change in enthalpy. All right, so there's a short little video that kind of introduces enthalpy. Oh, real quick, I want to talk about, no, that's good. We'll stop there for this video, okay? So here's where we're going to start going with thermochemistry, okay? So we're going to be studying the heats of reaction, and what are those heats really telling us? It's the difference, okay, between the energy needed for the bonds of the reactants to stay together versus the bonds of the products to stay together.